In this session we'll talk about moment of inertia. What is moment of inertia? Moment of inertia is a factor which measures the strength of a section. So for example, if we have the following two sections, this one is 24 by 94 and this is 12 by 96. First question is, which section is stronger? I'm assuming that you'll say this is stronger because it is bigger. Good. But the other important question is that this one is stronger by how much? That is the issue. So moment of inertia is a measure for the strength of a section. Now, the equation of moment of inertia is, we don't need to derive the equation. It is bh cubed divided by 12. And if we take a sample or an example, this is an example. So we have a section and a beam, and this section has a width of 3 inches and a height of 10 inches. To calculate the moment of inertia about x-axis, it will be b. B will be the measurement that is parallel to the axis that we are taking moment of inertia about. So b will be 3 in this case, and h will be the measurement which is perpendicular to the axis that we are taking the moment of inertia about, which is 10 in this case. So we get a value of 250. Of course, this is in, if the measurement is in inch, then this will be inch to the power of 4, because b is inch. B will be measured in inch, and h will be in h cubed, so multiply, you add the power, so it becomes inch to the power of 4. Now we see I mentioned the moment of inertia about x-axis. It is also possible to take moment of inertia about y-axis. And so there are a couple of issues that we need to tackle here. Is the orientation of the section is important, and the shape of the section is important. This is a good comparison for you to be able to understand the moment of inertia. So if we were given a material that is 1 square meter, and we are asked to mold this into a shape that will give us the strongest possible moment of inertia. So if you do just half an inch by 2 inches, you will get this much, 0.33 inch to the power meter to the power of 4. If you change the orientation, this is about x-axis, this is the value ixx. If you change the orientation, you see the value is 0.02. So if you want to know how much is the difference, so 0.33, if you divide 0.33 divide by 0.02, this section is 16 times stronger than the first one. Now if you just go and do 1 meter by 1 meter, like so, you will see the moment of inertia is equal to 0.08. And again, if you want to compare this to the first one, so you do 0.33 divided by 0.08. So again, the first one is stronger, this one is stronger. The case one is stronger than the third by 4 something times. Now if you want to go and change the entire thing, like in the case number 4 here, and you mold this into this shape, then you will get a moment of inertia which is 2.79, and this one is stronger than the first one, 2.79 divided by 0.33 by 8 times. And if you compare this to the weakest one, which is 0.02, so if you do 2.79 divided by 0.02, So it's almost 140 times stronger than the weakest case. So again, you see here the strength or the moment of inertia is very much a factor of shape and orientation. Now if we take a look at this section, which is W18 by 119, and if you look at the table for the properties of the section, it will look for the moment of inertia about x and moment of inertia about y. So if we do that, so here is the section, and this is the moment of inertia about x, and this is moment of inertia about y. So you see the moment of inertia about x is 2190, that is inch to the power of 4, and moment of inertia about y is 253. And the orientation, keep in mind the orientation of a section is this. If you change the orientation of the section, then they will be switched. So here's the deal. So if we take this section like that, then moment of inertia about x, as you see, is equal to 253. Moment of inertia about y is 2190. So just keep an eye on this orientation, because this is important. Like I said, the shape and the orientation are important in the case of moment of inertia, and this is why you see most of the I-beams or C-beams are in this orientation and not in this orientation. Just true. So that this makes sense to you in the future. Okay, now let's try to do an example to implement. And of course I forgot to mention this is a simple section. In this case it is an I-beam. It is an I-beam, but most of the time you will not see a single section. It will be a compound section. It will be a group of sections attached to each other. So for that one, the equation will be, for Ix is this, as you can see, and for Iy it is the one below. So let's try an example, and here is an example. Let's work on this example. In this example you have a section, an I-beam which is flipped like that, W18 by 97, and you have a steel plate 1 inch by 32, and you have another steel plate which is 2 by 16. So for plates we don't need to go to table, but for this section we need to go to tables and get the values, these values. So for section W1897 you'll find the area is 28, thickness of the web, this one, is 0.535 inches, and Ix, moment of inertia about x, and the orientation of the beam being like that, is 1750, and Iy is 201. But keep in mind this is rotated, so it will be switched. So here's the section, and of course we need to need the centroid before we start to work on the moment of inertia. And if you remember, in the case of centroid we always had our measurement x and y from the reference point, but now the measurement will be from the location of the centroid of the entire section. And this entire section, y distance is this one, 17.1, and the x is at the 0, so x means x bar is equal to 0 and y bar is equal to 17.1 inch. So this is now you need to calculate this yourself, but we'll assume this is given to us for now, just to demonstrate how to calculate the moment of inertia about x and moment of inertia about y. So again, step number 1 is we need to, if you look at the equation, from the equation will give us we'll use a template for this equation, and that equation So here is the template, in which we'll have the area column and moment of inertia for the component about x, and the y distance. dy means the y distance from the centroid of the component to the centroid of the entire section, and this is multiplication, and this is moment of inertia for the component about y, and this is the x distance. Dx means the x distance from the centroid of the component to the centroid of the entire section, and this is multiplication. So we'll use this template to do the calculation, but the important thing again is to know the dy distance and dx. The x and y distances, that's one. The second thing is the orientation of the moment of inertia. See, in this case we have this beam is oriented, the original orientation of this beam will be like that in the tables. So this one is switched, so it means that you switch x by y and y by x. So it means ix becomes iy and iy becomes ix. And if you look at the properties of the section, you see the ix is equal to 1750 and iy is equal to 201. So you just switch them because the shape in your example is switched. So now we'll focus on measuring the distance between the centroid of the section and the centroid of the entire thing. So let's do this on enlarged. There. So this is the section. This is the W18. So we need to get the distance So I would like to get the distance from here, this distance, so I need to measure the distance for dy1, which is this one, and this is from the centroid here to the centroid of the entire thing here. So to approach this is I need, if I'll make this a bit larger, if I make this a bit larger, so meaning I need the distance from the middle here till here. First, this is the first thing, and I subtract it from this distance, so I get this distance. So the first distance, this one, is composed of half of the thickness of the web here, plus the height of the plate, plus height of this plate. So if you look at the calculation here, you will see in the calculation part, let's make this a bit smaller. So I have here half the thickness of the web and the plate 32 inches and the other plate 2 inches, and I subtract this from 17.1. That will be the, so if I go back to the sketch itself, so that will give me the distance from here to here. If you can apport this differently to get the same value, that should be fine also, but this is how I will see this calculation. Number the same value at the end, that is still okay. And the x distance is 0 because the centroid here is coincides with the intersection of x and y, which is the location of the centroid of the entire thing. Now for the plate part, again, this you don't need to get the measurement from a table because the plate is straightforward. Of course, the area is, we got the area from the table here, by the way, and we talked about this and talked about this. For this one, you need to, the area do multiplication is 1 inch by 32, and that is what these numbers are. Now with the ix is you have to apply this equation, bh cubed divided by 12, and we said B is the measurement that is parallel to the axis we are taking moment of inertia about. That will be 1 inch, and so it will be h cube 1 inch multiplied by 32 cube divided by 12. For the y distance, now if you go back to the y distance here, it's 32 divided by 2. This is the middle of the components centroid, plus 2 minus 17. So if we go back to the sketch here, so we'd like to get the distance, this distance, dy2, from here to here. So meaning that I need to get this distance, so I have the entire distance here, divide by 2, I get this point from here to here, and then I subtract this from it, I get this distance. So that's what the calculations are. So say 32 divided by 2, that is the height of the plate, plus 2 to the bottom of the, and minus 17.1. That is the answer. Again, x, this is thing in the middle, so there is no x distance. This coincides. Now see, this plate is 2 by inch, but it is oriented differently. So again, the area is not a big deal. It is 2 multiplied by 16. We know this much. But for the moment of inertia about x, is B is the measurement parallel to the x-axis, to the axis that we are taking moments of inertia about, which is in this case 16. So it is 16, and the height is and the height will be this measurement, which is 2 inches. So if we go back to the measurements, the calculation, so you see we have B, which is 16, and h is 2 inches, and 12 is cube, of course, divided by 12. That will be h cube divided by 12. Of course, the y distance will be it is the distance between this and this, which is 2 divided by 2. So it's 2 divided by 2, so we go back to calculation. Sorry, we have to measure this from the entire section here. The distance is from here to here, so it will be the entire distance, which is 17, minus this distance, which is 2 divided by 2. Let's take a look at the so 17 minus 2 divided by 2. Of course, the y, moment of inertia about y, you have to reverse this, because now it is like that. So this will be, this is y. So the measurement that is parallel to the y-axis is this 2, and the perpendicular is 16. So that's why we say b h cubed divided by 12, and b is equal to 2 inches, and h is equal to 16 inch cubed divided by 12. And of course, the distance here between the x distance between the centroid and of the entire section and the centroid of the component is 0, as you can see here. And once we get this value, now all we need to do is to do the calculation here. So if you look at your y-axis again, use the sum of all moment of inertia about axis, which is this one, plus sum of all areas multiplied by dy square, which is this one, So put these together, you get this value. This is Ixx, and for Iyy, it is the sum of all moments of inertia about y, which is this one, and plus the sum of this value, which is 0. So the answer is 2435.